This chapter's on differential equations, which is another way of saying an equation with a derivative in it. So we'll first look at different order differential equations, but the first one we're going to look at is just a basic first order differential equation, which means that we only have the first derivative within the equation. If we talk about second order differential equations, we'll see a second derivative in the equation. In the case of the first just idea of a separable differential equation, we're looking at a familiar equation, let's say dy dx, or the derivative is equal to x squared. So an expression like this. With u substitution, we started to talk a little bit about how dy and dx are variables and they represent a small change in y and a small change in x. We'll see that more as a physical representation in the Euler's method lesson, which is the next lesson. But for now, we're going to treat dy and over dx as a fraction. And when we say separable, we mean that we're going to separate the y's on one side and the x's on the other. So when you're looking at dy over dx, one way to bring the dx over is to multiply both sides by dx. So times dx on both sides. That's going to leave us with just dy on the left and x squared dx. At this point, if I want to solve for y, because the whole goal will be given a differential equation or an equation with a derivative in it, we're asked to find the solution, which is the original function. What is y equal to? So that involves now integrating both sides. So when I integrate dy, there's a 1 here, like on our basic integration quiz, and we get y equals 1/3 x cubed. And because this is a general, they're asking for a general solution, we'll have a plus c at the end. Remember that this represents a whole family of functions whose derivative, when I take it, brings me back to x squared, which when I double check my work, the derivative of 1/3 x cubed is x squared. The derivative of c is just 0. So that nothing about that is unfamiliar except for the very beginning where we separated dy and dx. Okay, so now we look at an example where the complexity of your dy dx function increases a little bit. So we have 1 plus x on one side, or sorry, dy dx on one side, and then 1 plus x times 2 plus y on the other side. And so once again, our goal is to solve for y, solve for the original function given a differential equation, given an equation with a derivative in it. So what our first step will be is to separate and move x to the right and move y to the left. So that's going to involve multiplying both sides by dx and then asking ourselves, well, how would we move? Right now we have a product of 1 plus x times 2 plus y times dx. So right now I'll just write that out as our step, and let me keep it in blue. So dy equals 1 plus x times 2 plus y times dx. So we want to keep the 1 plus x and the dx on one side. We're going to go ahead and divide over 2 plus y to the other side. In doing so, we now have 1 over 2 plus y on the left, dy. Everything's with respect to y. On the other side, the 2 plus y cancels out, and we have 1 plus x dx. Now when we integrate, at this point, so we want to, this whole part right here was separate x and y. And then the next stage will be, we will integrate. So integrate both sides. With the 1 over 2 plus y, so long as the bottom is linear, we can reverse our u substitution. Either apply u substitution, let u equal 2 plus y because its derivative is just a constant. And it might be easier for us to see it that way as the integral of 1 over u. Or, as so long as you guys recognize the bottom as something linear, what you can do is just reverse the derivative in your head. The derivative of what would get you 1 over 2 plus y? The derivative of ln of 2 plus y would give you 1 over 2 plus y. And I want to double check this. The reason why I say it's linear is because when I take the derivative of 2 plus y, let's say I'm checking my work and I'm trying to see, well, does this really get me back to the original? I take the derivative of ln of 2 plus y and I get, and I'll write this off on the side, the derivative would be 1 over 2 plus y times the derivative of 2 plus y, which happens to be just 1. So that does work out. You want to be really careful. The highlighted portion, the way that I did this problem is only recommended, so I will make a note here. U sub in mentally or in your head only when argument of log is linear. So we want to be careful. If it's not linear, it does not work out that way. Okay, so ln of absolute value of 2 plus y. Now, the idea is that anytime we take a general antiderivative, we should be adding plus c to our antiderivative at this point right here. But let me explain why we usually don't put it on the side of the y. In a minute, we'll come back to that idea. So let's go ahead and on the right-hand side, find the general antiderivative of 1 plus x. The antiderivative of 1 is x. The antiderivative of x is plus 1/2 x squared. Now, on the right-hand side, we'll do the plus c. Let's talk a little bit about why we don't need the expression of plus c on the left-hand side. So in theory, let's say we did put a plus c on the left-hand side with the ln of 2 plus y. Now, if my goal is to solve for y anyway, I would be subtracting c to the other side. And so whatever this constant might have been, if I subtracted it over here to this constant, it would still remain just a constant. So rather than writing it on both sides, we usually keep it on the side of the independent variable, in this case, x. So in this problem, the goal was to solve for y at the very beginning. That was our goal. So now it's just becomes an algebraic equation where we're solving for y and undoing the ln. So when we think about how we can get rid of the ln, what should come to mind is the inverse, which is e. So we're going to take e to the power of ln of 2 plus y, e to the power of x plus 1/2 x squared plus c. So here we have, this is the step I want to make sure I explain really carefully to you guys. The e to the ln will undo each other. We're still left with the absolute value of 2 plus y. Don't drop the absolute value just yet. Leave that there. And then here we have e to the x plus 1/2 x squared plus c. That's all in the exponent. One thing that we can do, and I am going to recommend that we get comfortable with doing that, is recognizing that it's allowed for me to, using properties of exponents, separate e to the x plus 1/2 x squared from e to the c. And that's through multiplication. So let's think about that a moment. When you're using properties of exponents, if you have a multiplication problem with the same base, you can combine these two by adding your exponents. So in this case, I'm just reversing that. So at this point, we have the absolute value on the left, and then this over here on the right. Okay, so the e plus c, oftentimes with exponential equations, is called your initial condition, or what we call a. Okay, so we're going to redefine e to the c as a. So I'll call it let e to the c be equal to, or let's reverse that. Let a be equal to e to the c. So now our equation is absolute value of 2 plus y equals a times e to the x plus 1/2 x squared. And so how do we solve for absolute value of 2 plus y is equal to that? So what the absolute value represents is plus or minus. So we're gonna drop the absolute value, and our solution is going to be plus or minus a e to the x plus 1/2 x squared. Now, if we think about this, a can actually technically incorporate the plus or minus as well, since that just means it's a constant. So sometimes we think about a as also plus or minus, so we add the plus or minus right here to our expression for a. we can actually eliminate and make this a little bit more simplified. So if I eliminate the plus or minus here, but include it up above, and I'll highlight this, and include it up above here as a being equal to plus or minus e to the c. So just to clean up our expression a little bit. And lastly, we're going to subtract the 2 over to the other side. So y equals some constant a, e to the x plus 1/2 x squared, and then minus 2. That would be our general solution. Now, most of the times with separable differential equations, these are going to be huge problems on your free response questions. I can't think of one question for one part that is worth 6 out of 9 points, but usually with the separable differential equation, we see that because it's so involved in so many details to it, that we get problems that are worth 6 out of 9 points possibly on the free response, if we see this on the free response. So let's take a look at example 2, and right now we should be asking ourselves, well, this a, it feels a little bit incomplete. How do I solve for a, given that, so a is just saying that there is some type of constant. Now what we need is, when we were solving for general antiderivatives and we were given a initial condition, we could solve for the value of the constant. So that's what we need here, is an initial condition. So let's go to example 2. In example number 2, we're going to solve for y. And this time they're going to give us a solve for y given the initial condition of y of 1 is equal to 2. And again, this is what we refer to as initial condition. When I see that, I know, okay, now I have enough information to solve for constants. Okay, so that's initial condition. So we see a more complex differential equation, 3x squared y prime minus x equals 0. So the goal is to separate our x's and y's. Y prime, what I'm going to do with y prime is replace that with the differential dy over dx. So let's write that out as 3x squared y squared times dy over dx minus x equals 0. So if we go on to separate these two, we're going to go ahead and add x to the other side as our first step. And so when we do that, we get 3x squared y squared dy over dx equals x. We see that we can multiply dx by both sides to further get x by itself. And then finally, we have 3x squared y squared dy equals x dx. The question is, what would we do to separate the x's from the y's? And the x usually goes on the right, y is on the left. So we see that we have 3 times x squared times y squared times dy. So the last step would remain that we would divide both sides by x squared. And we can leave the 3 on either side. So I'll just go ahead and leave it on the left-hand side. So at this point, we have the x squareds cancel out. 3y squared dy is equal to 1 over x, if I simplify that, dx. And at this point, we've done our first duty, which is separate x and y. The next stage would be, we're going to integrate at this point. Integrate both sides. So with the free response question, it's important that we recognize separable differential equations, because the very first step is crucial. If we don't recognize that we're supposed to separate, then the rest of the problem is incorrect. And so this usually is awarded 1 or 2 points on the free response just for separating it. And then the next step involves a couple points. At this point, when we integrate both sides, we get we can pull the 3 out front, and then the antiderivative of y squared is 1/3 y cubed. And then again, we do the plus c over on the right. So the antiderivative of 1 over x is ln of the absolute value of x, and we're going to add plus c at the end of that. So over here, just simplifying things out a little bit, we have y cubed equals ln of the absolute value of x plus c. Now, at this point, I would recommend whenever you get to a point where you're trying to decide, okay, is it at this point that I solve for c, or should I solve further for y? To not overcomplicate what's going to happen to your c on the right, I would suggest at this point, you're going to plug in your initial condition. So this is, we've accomplished the integrating both sides. So now the next stage would be solve for c using IC, which is initial condition. Okay, at this point, I wouldn't solve for y, I would solve for c first. So going back, y1, remember the initial condition given, y1 equals 2 is your IC. Okay, so we're going to plug that in. If we plug 2 into y cubed, we get 2 cubed equals ln of the absolute value of 1 plus c. So when we do the absolute value of 1, we get 0. So remember, e to the what power is equal to 1, that is 0. So we get 8 is equal to c. We take this value and then plug that into c. So at this point, we have y cubed equals ln of absolute value of x and then plus 8. Usually when they say solve for y, it means that we're going to take the cube root and isolate y, so y is on one side on its own. So we're going to take the cube root of y and be left with y is equal to the cube root of ln of the absolute value of x plus 8. Okay, so that is our solution with the plus c solved for, or the constant solved for. So for example 3, I'd like you guys to try to hit pause on this and see if you can separate the variables for me. This would be our last example and quite an extensive one. So go ahead and see, after you write down the initial problem, see if you can separate the variables. So hit pause and separate. So we're gonna, again, the directions will say solve for y when y of 0 equals 1. So keep note that we have an initial condition, so we can solve for c. So initial condition to solve for c. So if you're a bit overwhelmed with it, keep going. If you guys want to try this on your own, I want you to hit pause and then see if you can solve it on your own. You can fast forward to skip over my speaking of this if you guys want to check to see if you got the right answer. Otherwise, if you would rather work through it with me, we're going to go ahead. We see we have one term here and two terms here. So the first thing is I'm going to subtract xy dx to the other side. I get e to the negative x squared, y squared minus 1 dy is equal to xy dx. And sometimes the functions aren't separable, meaning that no matter what I do algebraically, I can't separate the x's and y's. And that usually occurs when you have multiple terms. But in this case, we have two terms. It was easy enough to separate. And then after that, everything else is a product, which then means I can separate. So I'm going to divide e to the negative x squared to the other side and be left with y squared minus 1 dy on the left, because the e to the negative x squared canceled out. I have x over e to the negative x squared, or we'll fix that in a minute with the negative exponent, times y times dx. So that means I can divide both sides by y, and that's going to get us where we want, which is to get y on one side. So we currently have y squared minus 1 over y dy, and over on the left, the y's had canceled out. I'm going to fix that so that says x times e to the x squared. And I just realized when I moved this term over to the left. Hopefully some of you guys caught my mistake, that should have been minus over to the other side. So right here, this should be, and I'll add this here so you guys can see, this should be a minus sign right here, right? So let's go ahead and fix that. So minus x would be here as well. And let me highlight that so you guys see where my correction was. That's the minus sign there. And a negative here. Okay, at this point, all of this was separating. That's the part where we would have to separate x from y. Now the next stage is we're ready to integrate. When we integrate the left-hand side, I notice it's a basic integration type problem where if you notice there's a monomial at the bottom, so you can separate and say y squared over y is just y. And then minus 1 over y dy. Again, all I'm doing is dividing y into it so that I can take the antiderivative term by term. Over on the right-hand side, we'll work on this side by trying to figure out, okay, well, this does not look like a basic integration question. So the next move I do is this a u sub question? And when I look at this, the baby function could, for e, would be the argument is x squared. When I take its derivative, do I see its derivative somewhere here? And sure enough, I do. The derivative of something quadratic is linear, which is right here. And that's going to allow me to cancel out this x. So let's apply u sub here. So over on the left, keep in mind I haven't taken the antiderivative yet. We'll do that in a minute. Over on the right, we're going to simultaneously do this. So let u be equal to x squared. That's the baby function. So the derivative of u is du. The derivative of x squared is 2x dx. So let's rewrite this. Negative x we're going to leave alone. E to the x squared is u. And then if I had solved for dx to make that replacement, and so there's a dx right here. So if I divide both sides by 2x and replace my dx, I get du over 2x. And the whole goal of that, again, is so that I can eliminate or cancel out this x right here. So let's keep going. This is going to be equal to, I have a 1/2 right here that I'm going to bring out front. So 1/2 along actually with this negative is going to yield negative 1/2 out front. The integral of e to the u du, which is nice and simple to do now. So the whole goal of u sub is to simplify your integrand. So what's the antiderivative of e to the u? Is just itself, and then plus rc. We just have to remember to re-plug back in what u was, which in this case was x squared, plus c. Over on the left-hand side, so we've successfully integrated at this point. So this was all integrate. And remember, we integrate both sides. The left-hand side where we left off was just rewriting this so that we separated each one of the terms, and now we integrate term by term. So the integral of y is y squared over 2 minus ln of absolute value of y. And let's go ahead and move that all the way down to where we have our expression for negative 1/2 x squared plus c. Okay, so let's just carry this down. Y squared over 2 minus ln of absolute value of y. And that's a doozy of a problem, I know. So at this point, there's some questions that you won't be able to just isolate y. However, we did have enough information to solve for c with our initial condition at the beginning. So our initial condition was that y, so this is IC, initial condition, y of 0 is equal to 1. And let me just make sure that that was what I wrote down. Y of 0 is equal to 1. So at this point, this is going to be solve for c part. Okay, so at this point, we have 0 plugged in for x and 1 plugged in for y. So if I plug 1 in, I get 1/2 here. Ln of the absolute value of 1 equals, over on the left, we have negative 1/2 e to the 0 and then plus c. So in simplifying this, ln of 1 happens to be just 0. So we have 1/2 equals negative 1/2 plus c. So if I solve for c by adding 1/2 to the other side, I get c equals, yay, just a simple 1. So now what we do is we take where we left off in solving for c, we transfer that down, we get that the solution is y squared over 2 minus ln of the absolute value of y equals negative 1/2 e to the x squared, and then plus r1, which is the c. And again, that's what I had done to solve for c. And with this one, this is an expression where we can't isolate y with y squared and ln of y. So this is as far as we can go. We want to watch the directions. Sometimes they do say solve for y individually, so then that means that y would have to be isolated. I should clarify that at the beginning we should say let's change this direction just to say solve for the differential equation. So solve for differential equation. And so when they don't specify that, we don't necessarily have to isolate y. But if they say solve for y, that means that they do want y by itself.